A black hole 10 million times more massive than our star is tearing through space at 2.2 million miles per hour, leaving a trail of newborn galaxies in its wake. Another one is erupting with the power of 10 quintillion hydrogen bombs every single second, ripping its home galaxy apart from the inside. These are not theories. These are direct observations from the James Webb Space Telescope, and they are rewriting everything we thought we knew about the universe. If you are ready to witness the most violent cosmic events ever recorded, hit like and subscribe. Take a deep breath. We are diving into the abyss. Scientists thought black holes were anchored to their galaxies, locked in place by gravity so powerful that nothing, not even entire star systems, could break free. Then the James Webb Space Telescope aimed its instruments at a galaxy called the Cosmic Owl, 8.8 billion light-years away. What it found changed everything. A supermassive black hole was racing through space at 2.2 million miles per hour. That is 3,000 times faster than the speed of sound here on Earth. This was not drifting. This was fleeing. The black hole had been violently ejected from its home galaxy, and it was dragging something behind it. A tail, 200,000 light-years long, longer than our entire galaxy is wide. Inside that tail, gas was collapsing. Stars were forming. The runaway black hole was not just escaping. It was creating a trail of newborn galaxies as it tore through the cosmic void. How do you kick a black hole out of its galaxy? The forces required are almost unimaginable. A supermassive black hole contains the mass of millions or billions of stars compressed into a single point. Moving one requires more energy than 1 trillion supernovas. Yet here it was, rocketing through space like a bullet. The James Webb Telescope had opened a window onto the universe's first black holes, and what it revealed was stranger than anyone had imagined. But the little red dots were just the beginning. What came next was even more extreme. Deep in a region of space, nearly devoid of light, the James Webb Telescope found something that should not exist. A black hole 50 million times the mass of our star, sitting in a galaxy with almost no stars. This was not just unusual, this was impossible according to every model of black hole formation. The galaxy, called Abell 2744 QS01, appeared as it looked 13 billion years ago, just 800 million years after the Big Bang. At that age, galaxies should be packed with young stars. Black holes should be small, still growing from the remnants of the first stellar explosions. But this black hole was already enormous, and it was surrounded by darkness. Boyuan Liu from the University of Cambridge led the team that discovered the object. He said it was an interesting and important possibility that this could be a primordial black hole, not a black hole formed from a star. Not even a black hole formed from a collapsing gas cloud. A black hole that formed directly from density fluctuations, moments after the Big Bang itself. The idea of primordial black holes was first proposed by Stephen Hawking decades ago. He theorized that in the extreme conditions of the early universe, tiny variations in density could collapse into black holes without needing stars at all. These black holes would be ancient, older than galaxies, older than the first generation of stars. They would be relics from the very birth of the cosmos. If this black hole in Abell 2744 QS01 is primordial, it would rewrite our understanding of structure formation. It would mean the first black holes did not need stars. They did not need galaxies. They could form independently from nothing but the violent chaos of the Big Bang, and then grow rapidly by merging with each other in the dense early universe. Advanced simulations explored scenarios where massive black holes could exist in low stellar density environments so soon after the Big Bang. The simulations showed it was possible. If primordial black holes formed in sufficient numbers, they could merge and accumulate mass without relying on the collapse of stars. They could explain the supermassive black holes found in the early universe without requiring complicated theories. But there is another possibility. The black hole might not be primordial. It could have formed through direct collapse of gas, triggered by shockwaves from nearby galaxy interactions. This process, similar to the one that created the little red dots, could also produce massive black holes in regions without many stars. The debate is ongoing. What is clear is that this black hole challenges everything scientists thought they knew. Normal black hole formation theories struggle to reproduce these observations. The presence of such a massive object in a starless region forces scientists to consider alternatives they once dismissed as speculative. The discovery also reopens one of the most tantalizing ideas in theoretical physics. If primordial black holes exist in sufficient numbers, they might account for some or all of the missing mass in the universe. They could be dark matter, not exotic particles, not mysterious fields, just ancient black holes, invisible and undetectable, holding the universe together. Even if they are not dark matter, their presence reshapes our timelines of galaxy evolution and the conditions of the early universe. The James Webb Telescope had found a candidate for one of the oldest objects in existence. Further observations will be needed to confirm it, but the implications are already staggering, and the strangeness does not stop there. Black holes do not just consume, they eject. When matter spirals into a black hole, some of it gets funneled into jets that shoot out perpendicular to the accretion disk. These jets travel at nearly the speed of light, carrying energy across thousands of light years. Scientists have studied these jets for decades, but the James Webb Telescope revealed something no one expected. The jets were wobbling, not slightly, not randomly. They were precessing in a controlled, spiral pattern, carving shapes into the gas around them. Astronomers had seen jets wobble before on smaller scales, but never like this. Never so extended, never so powerful. The black hole at the center of galaxy VV340a was driving this phenomenon. As the jets swept across the galaxy, they pushed gas outward in spiral waves. The pattern was visible in both optical and infrared wavelengths. It looked like a cosmic pinwheel, spinning slowly across thousands of light years. Why were the jets wobbling? The answer lies in the black hole's spin axis. If a black hole is tilted relative to its accretion disk, the jets will precess like a wobbling top. This happens when black holes merge, or when they consume material at an angle. The wobble is a record of past violence. The jets from VV340a were not just wobbling, they were also incredibly collimated. That means they stayed tightly focused over enormous distances instead of spreading out. Scientists expected jets to diffuse as they travelled. These did not. They maintained their structure across the entire visible range of the telescope's instruments. Vivian Yu, one of the researchers studying the jets, said the emission was far more extended and coherent than expected. The James Webb Telescope had revealed structure that previous instruments could not detect. The jets were not simple streams of matter. They were complex, organized, and far more powerful than models predicted. The energy carried by these jets was stripping the galaxy of its star-forming gas. Every time the jets swept through a region, they heated the gas to millions of degrees and blasted it into intergalactic space. The galaxy was losing the raw material it needed to create new stars. In astronomical terms, it was being slowly killed. But the jets were not uniform. They pulsed, sometimes stronger, sometimes weaker, creating waves of pressure that rippled through the surrounding gas. These pulses matched the rhythm of the black hole's feeding cycle. When the black hole consumed more matter, the jets grew brighter. When feeding slowed, the jets dimmed. The galaxy was watching its own destruction unfold in real time. Optical telescopes captured cooler gas pushed thousands of light years from the core. Infrared observations from the James Webb Telescope revealed superheated coronal gas close to the black hole. Together, they showed the full scope of the devastation. This was not a snapshot. This was a process. A slow, ongoing catastrophe. Scientists believe these wobbling jets may be common in the early universe, where galaxy mergers were more frequent. If that is true, then many galaxies in the distant past were shaped by this kind of violence. The smooth, orderly galaxies we see today are survivors. They are the ones that endured. But even survivors carry scars, and the James Webb Telescope is finding those scars everywhere it looks. At the tip of the runaway black hole's tail, something glowed, a bright region where gas was being compressed so violently it radiated across multiple wavelengths. The James Webb Telescope's instruments identified it immediately: a bow shock, the cosmic equivalent of a sonic boom. When an object moves through gas faster than the speed of sound in that gas, it creates a shockwave, the same physics that produces a thunderclap from a lightning bolt or a boom from a supersonic jet. But this was not air. This was intergalactic gas, and the object creating the shock was a black hole 10 million times more massive than our star. The bow shock was enormous. It stretched across thousands of light years, glowing in infrared and visible light. The gas ahead of the black hole was being pushed aside at hundreds of thousands of miles per hour. Behind the shock, in the black hole's wake, the gas was cooling and collapsing into stars. Pieter van Dokkum, who confirmed the discovery, said the evidence for a supersonic bow shock was very strong, bordering on overwhelming. The velocity measurements were clear. The spectral signatures matched predictions perfectly. There was no doubt about what was happening. A runaway black hole was ploughing through space, leaving a trail of destruction and creation in its wake. The bow shock revealed how fast the black hole was moving. By measuring the temperature and density of the compressed gas, scientists calculated the black hole's speed, 2.2 million miles per hour. That is 1,000 kilometers per second, fast enough to cross the distance from Earth to our moon in less than 4 minutes. The shockwave was not just compressing gas, it was heating it to tens of thousands of degrees. At those temperatures, hydrogen atoms broke apart into charged particles. The gas became ionized, glowing with a distinctive light that the James Webb Telescope's instruments could detect. This glow traced the exact path of the black hole. Inside the bow shock, conditions were perfect for star formation. The compressed gas was dense enough to collapse under its own gravity. The James Webb Telescope detected bright regions where new stars were already forming. These stars were less than a few million years old. They were born from the chaos of the black hole's passage. But the bow shock also told scientists something else. The black hole was not slowing down. If it were, the shock would be weakening. Instead, it was maintaining its intensity. The black hole had enough momentum to keep moving for billions of years. It might never return to its home galaxy. The discovery of a bow shock was the final piece of evidence needed to confirm this was a true runaway. Without the shock, scientists could not rule out other explanations. With it, there was no doubt. This black hole had been violently ejected, and it was still travelling at escape velocity. The James Webb Telescope's ability to capture the bow shock in such detail was unprecedented. Earlier telescopes saw hints of the tail, but could not resolve the shockwave itself. Only the James Webb Telescope had the sensitivity and resolution to confirm what was happening. It turned a candidate into a confirmed discovery, and the story of this runaway black hole was far from over. 200,000 light years. That is how long the tail behind the runaway black hole stretched. Longer than the width of our entire galaxy. And inside that tail, something extraordinary was happening. Stars were forming. Not just a few scattered clusters. Entire regions of star formation, strung out like beads on a cosmic thread. The black hole was not just fleeing, it was creating. Every pocket of gas it disturbed, every shockwave it left behind, became a nursery for new stars. The James Webb Telescope captured these star-forming regions in infrared light, revealing their youth and intensity. Some were less than 1 million years old. This was not supposed to happen. When galaxies collide and black holes get ejected, the expectation is destruction. Gas gets heated and dispersed. Star formation shuts down. But this runaway black hole was doing the opposite. It was triggering star formation on a scale rarely seen. How? The answer lies in the physics of shock waves. When the black hole plowed through intergalactic gas, it compressed it. Compression increases density. Higher density means stronger gravity. Once the gas became dense enough, it collapsed into stars. The black hole's violence became a catalyst for creation. Each star-forming region in the tail represented a potential future galaxy. If the regions survived long enough, they could accumulate more gas, form more stars, and eventually evolve into independent dwarf galaxies. The runaway black hole was not just moving through space, it was seeding the universe with the building blocks of new galaxies. Scientists estimate there are thousands of young stars in the tail, maybe tens of thousands. The exact number is hard to determine because the tail is so long and the stars are so young. But the James Webb Telescope's infrared instruments revealed their heat signatures clearly. They were there, they were real, and they were growing. The gas in the tail was not uniform. Some regions were denser than others. The densest regions collapsed first, forming the brightest stars. Smaller regions formed less massive stars. The variation created a spectrum of stellar masses, similar to what scientists see in normal star-forming galaxies. But unlike normal galaxies, these stars had no central black hole to orbit. They were orphans, born in the wake of a fleeing giant, with no home galaxy to anchor them. Their future was uncertain. Would they stay together and form a new galaxy? Or would they drift apart, scattered across the cosmos? The James Webb Telescope also detected organic molecules in some of the star-forming regions, complex carbon-based compounds that form in the dense, cool gas surrounding young stars. These molecules are the building blocks of life, not life itself, but the raw materials that could one day lead to it. This discovery raised a profound question. If a runaway black hole could trigger star formation and create the conditions for organic chemistry, could it also create the conditions for life? Could there be planets forming in the tail, orbiting stars born from cosmic violence? Scientists do not have answers yet. The tail is too far away and too young for detailed planetary surveys. But the James Webb Telescope has proven that even in chaos, creation is possible. Even in destruction, new beginnings emerge. And the universe is full of black holes. If runaway events like this happen regularly, then the cosmos might be dotted with trails of orphaned stars, each one a reminder that violence and creation are two sides of the same coin. But the next discovery makes even this seem small. In the chaotic early universe, conditions were perfect for black holes to grow. Gas was everywhere. Galaxies were smaller and more densely packed. Collisions were common. And in that chaos, black holes went on a feeding frenzy that scientists are only now beginning to understand. New simulations from Maynooth University revealed how it happened. Daxel Mehta, a researcher leading the study, explained that the first generation of black holes grew incredibly fast, ballooning to tens of thousands of times the mass of our star in just a few 100 million years. This was not slow accumulation. This was explosive growth. The key was the environment. In the early universe, gas clouds were pristine. They had not yet been enriched with heavy elements from dying stars. This primordial gas was smooth, cool, and easy to compress. When it collapsed, it did so efficiently, funneling material directly into black holes at astonishing rates. Traditional models assumed black holes could only grow slowly. The accretion rate was thought to be limited by radiation pressure. As gas falls into a black hole, it heats up and emits light. That light pushes against incoming gas, slowing the process. This is called the Eddington limit, and it sets a theoretical cap on how fast black holes can grow. But the simulations showed the early universe did not follow those rules. In the dense, chaotic conditions shortly after the Big Bang, gas could fall into black holes faster than radiation could push it away. The feeding frenzy exceeded the Eddington limit. Black holes grew at super Eddington rates, doubling their mass in timescales measured in thousands of years instead of millions. This explains the puzzling observations made by the James Webb Telescope. Astronomers found massive black holes existing far earlier than theories predicted. Some of these black holes were already billions of times the mass of our star less than 1 billion years after the Big Bang. Standard models could not account for their size, but the new simulations could. The chaotic early universe was not just creating black holes, it was supercharging them. Every galaxy merger, every gas cloud collision, fed the black holes at the centers of young galaxies. They consumed everything within reach, growing from modest seeds into the supermassive monsters we see in modern galaxies. The James Webb Telescope's observations confirmed these findings. The little red dots, the starless monster, the massive black holes in the early universe, they all pointed to the same conclusion. Black holes in the early universe grew faster than anyone thought possible. They did not need billions of years, they needed millions, maybe less. This rapid growth had consequences. Black holes that grew too fast began to influence their host galaxies. They heated gas, preventing it from collapsing into stars. They launched jets that cleared out surrounding material. In some cases, they destroyed their galaxies from the inside, leaving behind dead husks with no star formation. But in other cases, the feeding frenzy triggered star formation. The same shock waves that cleared gas from some regions compressed it in others. The result was a complex dance of creation and destruction, with black holes at the center, orchestrating everything. Scientists now believe that every supermassive black hole in the modern universe went through a feeding frenzy phase. Our own galaxy's central black hole, Sagittarius A star, likely consumed massive amounts of gas in its youth. The difference is that we are seeing it now, billions of years later, when it has settled into a quieter state. The James Webb Telescope is giving us a window into that violent past. It is showing us what our galaxy looked like when it was young, what all galaxies looked like when the universe was still wild and untamed. And the more scientists look, the more they realize the early universe was far stranger than they ever imagined. Stars die and leave behind black holes. That is the traditional story. A massive star exhausts its fuel, collapses under its own gravity, and forms a black hole a few times the mass of our star. Over billions of years, these black holes merge and accumulate gas, growing into the supermassive giants found at the centers of galaxies. But the James Webb Telescope revealed a different path, a shortcut, a way for black holes to form without stars at all. Scientists call it direct collapse, and it changes everything we thought we knew about black hole formation. In the early universe, before the first stars enriched the cosmos with heavy elements, there were massive clouds of pristine hydrogen and helium. These clouds were smooth, cool, and fragile. Normally, they would fragment into smaller clumps that collapse into individual stars. But under the right conditions, they could skip that step entirely. If a cloud was massive enough and dense enough, and if radiation from nearby sources prevented it from fragmenting, the entire cloud could collapse at once, not into a star, into a black hole. A black hole that would be born with a mass thousands or even millions of times greater than our star. No stellar phase, no supernova, just pure gravitational collapse. The James Webb Telescope found evidence of this process in the little red dots and the starless monster. These objects matched the predictions of direct collapse models perfectly. They were massive, compact, and surrounded by dense gas. They showed no signs of star formation. They were pure black holes, born from collapsing clouds. Fabio Pacucci's simulations confirmed the theory. He created virtual models of direct collapse black holes and compared them to the James Webb data. The match was perfect. Every feature, from the weak X-ray emission to the high ionization lines, fit the direct collapse scenario. No other model came close. This discovery solves one of cosmology's biggest mysteries. How did supermassive black holes get so big, so fast? The answer is, they did not grow from small seeds. They were born large. Direct collapse gave them a head start. From the moment they formed, they were already massive enough to dominate their surroundings. But direct collapse is rare. It requires specific conditions. The gas must be pristine, the cloud must be massive, and nearby radiation must suppress star formation without disrupting the cloud. In the modern universe, these conditions almost never occur. But in the early universe, they were common. Galaxy collisions triggered shockwaves that compressed gas into massive clouds. Intense radiation from the first stars and quasars bathed those clouds in light, preventing fragmentation. The result was a population of direct collapse black holes scattered across the early universe, growing rapidly and shaping the galaxies around them. The James Webb Telescope is witnessing this process in real time. It is catching direct collapse black holes in the act, still wrapped in their gas cocoons, still feeding, still growing. These observations are providing scientists with a direct window into the birth of supermassive black holes. And the implications go beyond black holes. If direct collapse was common in the early universe, it means the first galaxies formed differently than scientists thought. Black holes came first, then stars. The black holes shaped the galaxies, not the other way around. This flips the traditional narrative. For decades, astronomers assumed galaxies formed stars, and those stars produced black holes. But the James Webb Telescope is showing us that black holes may have come first. They may have been the seeds around which galaxies formed. The universe is revealing its secrets, one discovery at a time, and every secret leads to a deeper mystery. The wobbling jets from the black hole in VV340a were not random. They were creating a pattern, a spiral, a cosmic pinwheel carved into the gas of an entire galaxy. The James Webb Telescope captured this structure in stunning detail, revealing layers of complexity no one had seen before. The spiral was enormous. It stretched across thousands of light years, with each arm representing a different pulse of energy from the black hole's jets. As the jets wobbled, they swept through the galaxy like a lighthouse beam, heating gas in spiral waves. The result was a pattern that looked almost artistic, like a painting made of light and violence. Scientists had never seen anything like it. Spiral patterns are common in galaxies, usually created by the rotation of stars and gas. But this spiral was different. It was driven by jets, by energy pouring out of a black hole at nearly the speed of light. It was a record of the black hole's activity, written in glowing gas. Each arm of the spiral marked a moment in time. The outermost arms were the oldest, created when the jets first began wobbling. The innermost arms were the youngest, still being carved by the jets in real time. By studying the spacing between the arms, scientists could calculate how fast the jets were precessing. The answer was surprising. The jets were wobbling slowly. One full rotation took millions of years, but because the jets moved at nearly the speed of light, they could sweep across the entire galaxy in that time. The slow wobble created a tightly wound spiral, with each arm separated by just a few hundred light years. The spiral was not just beautiful, it was deadly. Every time the jets swept through a region, they stripped it of star-forming gas. The galaxy was being systematically sterilized, one spiral arm at a time. In a few 100 million years, the entire galaxy would be devoid of the raw materials needed to create new stars. But the spiral also revealed something about the black hole's history. The wobble was caused by a misalignment between the black hole's spin axis and its accretion disk. This misalignment likely resulted from a past merger. The black hole had consumed another black hole, and the collision had tilted its spin. The James Webb Telescope's instruments detected variations in temperature and density along the spiral arms. Some regions were hotter than others, some were denser. These variations matched the pulsing of the jets. When the black hole fed more actively, the jets grew hotter and brighter. When feeding slowed, the jets dimmed. The spiral was a timeline of the black hole's feeding history. Researchers also found evidence of shock fronts at the edges of the spiral arms. These were boundaries where the fast-moving gas from the jets collided with slower-moving gas in the galaxy. The collisions created compression zones where gas piled up, glowing brightly in infrared light. The shocks were not uniform. They varied in strength depending on the angle of the jets and the density of the surrounding gas. In some regions, the shocks were strong enough to trigger brief bursts of star formation before the jets heated the gas too much. In other regions, the shocks simply dispersed the gas, scattering it into intergalactic space. The cosmic pinwheel was a reminder that black holes do more than consume. They shape, they sculpt, they leave their mark on everything around them. The galaxy VV340a would never be the same. The black hole at its center had rewritten its structure, carved a spiral into its gas, and sealed its fate. And this galaxy was not unique. The James Webb Telescope is finding similar patterns in other galaxies across the early universe. Wobbling jets, spiral structures, galaxies being reshaped by the black holes at their centers. The universe is more dynamic than anyone realized, and the James Webb Telescope is showing us just how much violence is hidden in the beauty of the cosmos. For decades, scientists suspected that primordial black holes could be dark matter, the mysterious, invisible substance that holds galaxies together. Dark matter makes up 85% of all matter in the universe, yet no one has ever detected a single particle of it. What if it was never particles at all? What if it was black holes? The idea dates back to Stephen Hawking. He proposed that tiny black holes could have formed in the first fraction of a second after the Big Bang, when the universe was so dense that quantum fluctuations could collapse directly into gravitational singularities. These primordial black holes would be ancient, invisible, and scattered throughout the cosmos. The discovery of the starless monster in Abell 2744 QSO1 reignited this possibility. If massive black holes can form without stars, then smaller primordial black holes might be everywhere, too small to detect individually, but collectively massive enough to account for dark matter. The math works. If primordial black holes formed with masses ranging from a fraction of our star to thousands of times its mass, they could explain the gravitational effects we observe. They would pull on galaxies without emitting light. They would bend space-time without producing radiation. They would be dark matter in the most literal sense. But proving this theory is difficult. Primordial black holes do not emit light. They do not interact with normal matter except through gravity. The only way to detect them is through their gravitational influence. Scientists look for microlensing events, where a primordial black hole passes in front of a distant star and briefly magnifies its light. So far, the results are inconclusive. Some microlensing events have been detected, but not enough to account for all dark matter. Either primordial black holes are rarer than predicted, or they exist in a mass range that current surveys cannot detect. The James Webb Telescope is helping by observing the early universe, searching for indirect signs of primordial black hole activity. One clue comes from the distribution of galaxies. If primordial black holes were common, they would have influenced how galaxies formed. They would have acted as gravitational seeds, pulling in gas and triggering early star formation. The James Webb Telescope is testing this by mapping the large-scale structure of the universe in its infancy. Early results suggest that galaxy formation happened faster than standard models predict. This could be evidence of primordial black holes, or it could be evidence of something else entirely. The debate is ongoing, and every new discovery from the James Webb Telescope adds another piece to the puzzle. If primordial black holes are dark matter, it would solve one of the biggest mysteries in physics, but it would also raise new questions. How many primordial black holes exist? What size are they? How did they form? And most intriguingly, could some of them still be growing? The James Webb Telescope is not designed to detect primordial black holes directly, but it is uncovering the conditions of the early universe where they would have formed. It is showing scientists what the cosmos looked like when primordial black holes were being born, and it is revealing that the early universe was stranger than anyone imagined. Dark matter might not be a particle. It might not be a field. It might be ancient black holes, invisible and eternal, holding the universe together from the shadows. The James Webb Telescope is bringing us closer to answering that question. But even if primordial black holes are not dark matter, their existence would still rewrite the history of the cosmos. Black holes do not just destroy stars. They destroy entire galaxies. The James Webb Telescope is revealing the full extent of this devastation, showing how black holes shut down star formation and leave galaxies as empty husks, doomed to fade into darkness. The process is called quenching. When a black hole feeds actively, it launches jets and winds that heat the surrounding gas to millions of degrees. Hot gas cannot collapse into stars. It expands and disperses, leaving the galaxy with nothing to fuel new star formation. Within a few 100 million years, the galaxy dies. The black hole in VV340a was caught in the act of quenching. The James Webb Telescope observed gas being expelled at hundreds of thousands of miles per hour, stripped from the galaxy and blasted into intergalactic space. This was not slow leakage. This was violent ejection. The galaxy was losing its future in real time. Scientists estimate that the black hole was expelling gas at a rate of hundreds of times the mass of our star every year. At that rate, the galaxy would run out of star-forming material in less than 1 billion years. After that, it would produce no new stars. It would slowly dim as its existing stars aged and died. This process is common. The James Webb Telescope has found evidence of quenching in galaxies across the early universe. Some galaxies are already dead, their star formation shut down by black holes less than 2 billion years after the Big Bang. They appear as red, compact objects filled with old stars and devoid of the blue light from young ones. These dead galaxies are smaller than modern galaxies. They are denser, with stars packed closer together. They look like the cores of modern elliptical galaxies, frozen in time. Scientists call them red nuggets, and they represent the endpoint of black hole quenching. But not all galaxies die the same way. Some are quenched gently, with black holes slowly heating gas over billions of years. Others are quenched violently, with sudden bursts of energy that clear out gas in a single catastrophic event. The James Webb Telescope is finding both types, revealing the full spectrum of galaxy death. The violent quenching events are often triggered by galaxy mergers. When two galaxies collide, their central black holes eventually merge, releasing enormous amounts of energy. This energy drives powerful winds that sweep through both galaxies, expelling gas and shutting down star formation. The result is a single dead galaxy, larger than either of the originals, but devoid of life. The gentle quenching events are more subtle. They occur in isolated galaxies, where black holes feed steadily over long periods. The jets and winds are weaker but persistent. Over time, they heat enough gas to halt star formation. The galaxy does not die suddenly. It fades slowly, like a candle burning out. The James Webb Telescope is also finding galaxies that resist quenching. These are galaxies where gas continues to flow inward despite the black hole's activity. They maintain star formation by replenishing their gas supply from the surrounding intergalactic medium. But even these galaxies are on borrowed time. Eventually, the black hole will grow powerful enough to expel all the gas. The discovery of widespread quenching changes our understanding of galaxy evolution. Galaxies do not grow forever. They have life cycles. They are born in bursts of star formation, they mature as gas runs out, and they die when black holes shut down their star factories. The James Webb Telescope is showing us every stage of this cycle. Our own galaxy is approaching the quenching phase. The black hole at its center is currently quiet, but it will not stay that way forever. In a few billion years, when our galaxy merges with the Andromeda galaxy, the central black holes will collide. The resulting energy release could quench star formation in the merged galaxy. The universe is full of dead galaxies, billions of them scattered across space, their stars slowly aging with no new ones to replace them. The James Webb Telescope is mapping this graveyard, showing us the ultimate fate of galaxies, and it is reminding us that nothing lasts forever, not even galaxies. The Cosmic Owl Galaxy is not one galaxy, it is two ring galaxies in the process of colliding, their shapes warped by gravity into structures that resemble eyes. But the James Webb Telescope revealed something even stranger. A third black hole, lurking in the gas between them, possibly born from the collision itself. Galaxy mergers are common in the universe. When two galaxies collide, their stars rarely touch. Space is so vast that individual stars pass by each other without incident. But the gas clouds collide violently, creating shock waves that compress gas and trigger bursts of star formation. And at the centers of the galaxies, the black holes begin a slow dance toward each other. The two black holes in the Cosmic Owl were already spiraling inward. In a few 100 million years, they would merge, releasing gravitational waves so powerful they would ripple across the entire universe. But before that could happen, a third black hole appeared. Scientists are still debating where it came from. One theory is that it formed directly from gas, compressed by the collision. The shock waves from the merging galaxies created dense clouds that collapsed into a black hole without forming stars first. This is the direct collapse mechanism, the same process that created the little red dots. Another theory is that the third black hole came from a smaller galaxy that merged with one of the Cosmic Owl galaxies earlier. It survived the first merger and was now caught in the gravitational chaos of the second. Either way, it was there, and it was complicating everything. Triple black hole systems are rare. Most galaxy mergers involve just two black holes. But when three black holes interact, the dynamics become unpredictable. They orbit each other in chaotic patterns, exchanging energy and momentum in ways that are nearly impossible to calculate. Sometimes, all three black holes merge. The resulting gravitational wave signal would be unlike anything ever detected, a complex pattern of peaks and valleys encoding the masses and spins of all three objects. Scientists are eagerly waiting for gravitational wave detectors to catch such an event. Other times, one black hole gets ejected. The three-body interaction creates a slingshot effect, where one black hole gains so much energy it escapes the system entirely. This is likely what happened to the runaway black hole in the Cosmic Owl. It was kicked out by a triple interaction, sent flying at 2.2 million miles per hour. The James Webb Telescope's observations support this scenario. The velocity of the runaway black hole matches the predictions for a three-body ejection. The bow shock at the tip of its tail confirms it is still moving at escape velocity, and the presence of the third black hole in the Cosmic Owl provides the missing piece of the puzzle. But the story does not end there. The two remaining black holes in the Cosmic Owl are still spiraling inward. In a few 100 million years, they will merge. The resulting black hole will be even more massive, possibly billions of times the mass of our star. It will dominate the merged galaxy, shaping its evolution for billions of years. The James Webb Telescope is watching this process unfold. It cannot see the black holes themselves, but it can see their effects on the surrounding gas. It can map the gravitational distortions, the heated regions, the jets, and winds. It is capturing a snapshot of a cosmic catastrophe in progress. Triple mergers may have been common in the early universe, when galaxies were smaller and more densely packed. The James Webb Telescope is finding hints of other systems where multiple black holes are interacting. Each one is a laboratory for testing our understanding of gravity, orbital dynamics, and black hole formation. The Cosmic Owl is just one example, but it represents a class of events that shape the universe we see today. Every supermassive black hole in every galaxy likely formed through multiple mergers. Each merger added mass, changed the spin, and influenced the host galaxy. The James Webb Telescope is revealing the details of this process, and with every discovery, the universe becomes stranger. The gas surrounding the little red dots was not just hot, it was ionized. Stripped of its electrons by radiation so intense it tore atoms apart. The James Webb Telescope measured the ionization levels and found conditions that should not exist outside the cores of the most active galaxies. Ionized gas glows. The electrons, ripped from their atoms, eventually recombine, releasing photons in specific wavelengths. By analyzing these wavelengths, scientists can determine the temperature, density, and composition of the gas. The data from the little red dots was shocking. The gas cocoons were hotter than the surfaces of most stars. Temperatures reached hundreds of thousands of degrees, hot enough to emit ultraviolet and X-ray radiation. This was not the gentle warmth of star formation. This was a radiation furnace, powered by black holes consuming gas at extreme rates. The radiation was not uniform. It varied in intensity and wavelength, creating layers of ionization. The innermost layers, closest to the black holes, were fully ionized. The electrons were completely stripped away, leaving bare atomic nuclei. Farther out, the radiation weakened, and only the outermost electrons were removed. This layered structure created a unique spectral signature. The James Webb Telescope detected emission lines from multiple ionization states of oxygen, nitrogen, and carbon. Each line corresponded to a specific layer of the cocoon, revealing its structure in exquisite detail. The radiation was also driving winds. Photons from the black holes carried momentum. When they collided with gas, they transferred that momentum, pushing the gas outward. This process, called radiation pressure, was strong enough to expel material from the cocoons at thousands of miles per hour. But the winds were not escaping. The cocoons were too dense. The gas was trapped, cycling through the inner layers where it was heated and ionized, then drifting outward where it cooled and recombined, only to fall back inward and repeat the cycle. The cocoons were pressure cookers with gas continuously churning. This churning created turbulence. The James Webb Telescope detected velocity variations across the cocoons, indicating chaotic motion. Some regions of gas were moving inward, others outward. The turbulence mixed the gas, spreading the heat and radiation evenly throughout the cocoon. The radiation furnace was also creating molecules. Despite the intense heat, pockets of cooler gas existed in the outer layers of the cocoons. In these pockets, atoms combined into simple molecules. The James Webb Telescope detected water vapor, carbon monoxide, and hydroxyl radicals. These molecules were fragile, constantly being destroyed and reformed. The presence of molecules was surprising. Scientists expected the radiation to destroy all molecular bonds, but the cocoons were so dense that molecules could form in shadowed regions, shielded from direct radiation. This discovery hinted that even in the most extreme environments, chemistry can occur. The radiation furnaces were also feeding the black holes. As gas in the cocoons lost energy through radiation, it cooled and spiraled inward. This created a feedback loop. The black holes consumed gas, generated radiation, heated the cocoons, and drove winds. But the winds could not escape, so the gas fell back inward and the cycle continued. Eventually, the cocoons would dissipate. As the black holes consumed more gas, the radiation would grow stronger, eventually overcoming the cocoon's gravity. The gas would be expelled, leaving the black holes exposed. At that point, they would become visible as quasars, the brightest objects in the universe. The James Webb Telescope is witnessing the transition. Some little red dots are already beginning to shed their cocoons. The radiation is breaking through, creating gaps in the gas. In a few million years, these objects will transform from red dots into blazing quasars. This transformation marks a critical phase in black hole evolution. The cocoon phase is temporary, lasting only a few million years, but it is essential. During this phase, black holes grow rapidly, accumulating most of their mass. Once the cocoons dissipate, growth slows dramatically. The James Webb Telescope is capturing this process in unprecedented detail. It is showing scientists how black holes transition from hidden seeds to visible giants, and it is revealing that the universe's most powerful objects spend their infancy wrapped in radiation furnaces. But the radiation is not the strangest part. What comes next pushes the boundaries of physics itself. Black holes warp space-time. This is not metaphor. This is measured fact. The closer you get to a black hole, the slower time moves relative to the rest of the universe. This effect, called gravitational time dilation, is a prediction of Einstein's general relativity, and the James Webb Telescope is seeing its effects across cosmic distances. The gas spiraling into the little red dots was moving at a significant fraction of the speed of light. At those velocities, time dilation becomes noticeable. The gas experienced time differently than observers watching from far away. What looked like a few million years of feeding to us might have felt like only thousands of years to the gas itself. This creates a paradox. When we observe the little red dots, we see black holes that have been feeding for millions of years. But from the perspective of the gas falling into those black holes, only a fraction of that time has passed. The gas is living in slow motion, stretched out by the warping of space-time. The James Webb Telescope cannot observe time dilation directly, but it can see the effects. The spectral lines from the gas show extreme redshift, indicating motion toward the black holes at velocities approaching the speed of light. This motion, combined with the gravitational redshift from the black hole itself, creates a distinctive signature. Scientists use this signature to estimate the black hole's mass. The stronger the gravitational field, the more space-time is warped, and the greater the time dilation effect. By measuring the redshift and comparing it to the gas's velocity, scientists can calculate how deep the gravitational well is. The results are stunning. Some of the little red dots contain black holes with gravitational fields so strong that time near the event horizon runs 10 times slower than time far away. If you could hover just outside the event horizon for 1 hour, 10 hours would pass in the rest of the universe. This has profound implications for black hole growth. As gas spirals inward, it spends more and more time, from our perspective, in the inner regions near the event horizon. It lingers, heated to extreme temperatures, radiating energy. This radiation carries away some of the gas's mass, reducing how much actually falls into the black hole. The time dilation effect also influences the appearance of the little red dots. The radiation from gas near the event horizon is stretched out by time dilation, shifting it to longer wavelengths. This contributes to the red color that gives the objects their name. The little red dots are red, partly because of their cocoons, and partly because of relativity itself. The James Webb Telescope is also observing time dilation effects in the jets from active black holes. The jets move at nearly the speed of light, creating extreme relativistic effects. Light from the jet is beamed forward, making the approaching side appear brighter than the receding side. This asymmetry is visible in the telescope's images. But the time dilation effects are not just academic curiosities. They have practical consequences for understanding black hole feeding rates. Scientists must account for relativistic effects when calculating how much gas is falling into black holes. Without these corrections, the feeding rates would be overestimated by factors of 10 or more. The warping of space-time near black holes also affects the orbits of nearby stars. In our own galaxy, astronomers have tracked stars orbiting the central black hole at velocities exceeding 5,000 miles per second. The orbits show clear signs of relativistic effects, including precession and time dilation. The James Webb Telescope is extending these observations to distant galaxies. It is measuring the motion of stars and gas near supermassive black holes, billions of light years away. The data confirm that general relativity holds even in the extreme conditions of the early universe. Time dilation near black holes is one of the strangest consequences of Einstein's theory. It means that time is not absolute. It flows at different rates depending on where you are and how fast you are moving. Near a black hole, time slows to a crawl. At the event horizon, it stops entirely from the perspective of a distant observer. The James Webb Telescope is showing us these effects in action. It is revealing a universe where time itself is flexible, warped by gravity into shapes we are only beginning to understand. And the deeper we look, the stranger it gets. The stars forming in the tail of the runaway black hole face an uncertain future. They were born from violence, forged in the wake of a fleeing giant, with no home galaxy to anchor them. They are orphans, scattered across the cosmos, and their fate depends on factors no one can predict. If the stars stay together, they could form a new galaxy. A small dwarf galaxy, perhaps, but a galaxy nonetheless. Gravity would bind them, and over billions of years they could accumulate more gas, form more stars, and evolve into a stable structure. The runaway black hole would become the seed of an entirely new cosmic entity. But if the stars drift apart, they will remain isolated forever. Individual stars wandering through intergalactic space, too far from each other to gravitationally interact. They would age alone, burning through their fuel, and eventually dying as white dwarfs, neutron stars, or black holes. They would leave no legacy. The James Webb Telescope cannot predict which scenario will occur. The tail is too young and too distant for detailed simulations, but it can observe the current state of the stars and estimate their velocities. Early data suggests they are moving slowly relative to each other, held together by their mutual gravity. This is a good sign. It means the stars have a chance of staying together. But the tail is also embedded in intergalactic gas, which exerts drag on the stars. Over millions of years, this drag could slow the stars down enough for them to fall back toward the runaway black hole's original galaxy. They could be reabsorbed. Another possibility is that the tail will fragment. Instead of forming one large structure, it could break into multiple smaller ones. Each fragment would contain a few thousand stars, gravitationally bound but isolated from the others. The result would be a chain of tiny satellite galaxies, each one a remnant of the runaway event. Scientists have found similar structures in other parts of the universe, streams of stars stretching across hundreds of thousands of light years, likely created by tidal disruption or ancient collisions. The tail behind the runaway black hole could become one of these streams, a fossil record of cosmic violence. The orphaned stars also face threats from their environment. Intergalactic space is not empty. It contains diffuse gas, cosmic rays, and radiation from distant sources. Over billions of years, these factors can strip planets from stars, erode atmospheres, and alter stellar evolution. If planets formed around any of the orphaned stars, they would experience extreme isolation. The nearest stars would be light years away, too far to observe with the naked eye. The night sky would be almost completely black, devoid of the rich tapestry of stars we see from Earth. Any civilizations that arose on such planets would have a fundamentally different view of the universe. But planet formation in the tail is uncertain. The stars are very young, still surrounded by protoplanetary disks of gas and dust. These disks are the raw material for planets. But the radiation from the runaway black hole and the turbulence from the bow shock could disrupt the disks before planets can form. The James Webb Telescope detected organic molecules in some of the star-forming regions in the tail. These molecules, including complex carbon compounds, are the building blocks of life. Their presence suggests that chemistry is occurring despite the harsh environment. Whether that chemistry can lead to biology is unknown. The orphaned stars also carry information about the runaway event. By analyzing their composition, scientists can determine the conditions in the original galaxy before the black hole was ejected. The stars are time capsules, preserving a record of a galaxy that no longer exists in its original form. The James Webb Telescope is continuing to monitor the tail. Over the coming years, it will track the motion of individual stars and measure changes in the star-forming regions. This long-term data will help scientists predict whether the orphaned stars will form a galaxy or drift apart. Either way, the runaway black hole has left its mark on the universe. It has seeded space with stars born from chaos, and those stars will burn for billions of years, a reminder that even destruction can create beauty. But beauty is not the only thing black holes create. When three black holes interact, the physics becomes chaotic. Orbital mechanics that work perfectly for two bodies break down completely. There is no stable configuration, no predictable outcome. The black holes exchange energy and momentum in a wild dance that can only be solved through computer simulations. The runaway black hole in the cosmic owl was likely ejected through a gravitational slingshot. This process happens when three massive objects orbit each other in close proximity. One of the objects, usually the least massive, swings close to the other two. The gravitational interaction transfers energy, accelerating the third object to extreme velocities. The energy for this acceleration comes from the orbital motion of the other two black holes. They slow down, spiraling closer together, while the ejected black hole speeds up and escapes. The total energy and momentum are conserved, but the distribution changes dramatically. One black hole gains enough velocity to reach escape speed. The James Webb Telescope observed the aftermath of this process. The runaway black hole was moving at 2.2 million miles per hour. The two remaining black holes in the cosmic owl were closer together than before. The system had reconfigured itself, sacrificing one member to stabilize the other two. Gravitational slingshots are not unique to black holes. The same physics applies to any three-body system. Space agencies use gravitational slingshots routinely to send spacecraft to the outer planets. A spacecraft flies close to a planet, gains energy from the planet's orbital motion, and accelerates to higher speeds without burning fuel. But the black hole slingshot was on an entirely different scale. The energies involved were billions of times greater. The velocities were thousands of times faster, and the consequences were permanent. The ejected black hole would never return. It was gone forever, condemned to wander intergalactic space until the end of time. The slingshot also affected the direction of the ejection. The runaway black hole did not move randomly. It was flung along a specific trajectory determined by the geometry of the three-body interaction. The James Webb Telescope measured this trajectory by tracking the bow shock and the tail. The data matched simulations of three-body ejections perfectly. Scientists can use the trajectory to reconstruct the original configuration of the black holes. By running the interaction backward in time, they can estimate the masses and orbits of all three black holes before the ejection occurred. This provides a snapshot of the system's history, revealing details that would otherwise be lost. The gravitational slingshot also explains why runaway black holes are rare. Most three-body systems do not eject a member. Instead, one black hole merges with another, and the third escapes with lower velocity. Full ejections require specific conditions: the right masses, the right orbits, and the right timing. These conditions occur infrequently, but when they do occur, the results are spectacular. The James Webb Telescope has confirmed only one runaway black hole so far, but simulations suggest there should be others. As the telescope surveys more galaxies, it will likely find additional examples. Each one will provide new insights into three-body dynamics and black hole interactions. The slingshot process also produces gravitational waves. When the black holes swing close to each other, they accelerate rapidly, creating ripples in space-time. These waves carry away energy, further altering the orbits. Future gravitational wave detectors may be able to catch the signal from a slingshot event as it happens. The James Webb Telescope is revealing the consequences of gravitational slingshots across cosmic time. It is showing scientists how galaxy mergers and black hole interactions reshape the universe. And it is proving that chaos, not order, drives much of cosmic evolution. The runaway black hole is just one example, but it represents a broader truth. The universe is not static. It is not predictable. It is wild, violent, and constantly changing. And the James Webb Telescope is capturing every moment. For every black hole the James Webb Telescope observes, there are likely dozens more hiding in the darkness, black holes that are not feeding actively, black holes surrounded by empty space, black holes that emit no light and leave no trace except their gravitational influence. Scientists call these dormant black holes. They represent the vast majority of the black hole population. Most black holes spend most of their time in this state, quietly drifting through space without consuming gas or producing radiation. They are invisible to telescopes, detectable only through their effects on nearby objects. The James Webb Telescope is helping scientists estimate how many dormant black holes exist. By observing active black holes in the early universe and measuring their feeding rates, scientists can calculate how long they remain active. The answer is surprising. Most black holes are active for only a small fraction of their lifetimes. A typical supermassive black hole might feed actively for a few 100 million years during its host galaxy's youth. After that, it goes dormant for billions of years. If the galaxy merges with another galaxy, the black hole might reactivate temporarily, but for most of cosmic history, it sits dark and silent. This means the universe is filled with dormant black holes, billions of them, scattered across galaxies, waiting for their next meal. Some will never reactivate. They will remain dormant until the stars in their galaxies die and the universe fades to darkness. The James Webb Telescope has found indirect evidence of dormant black holes by observing their host galaxies. Galaxies that were once active, with bright cores and powerful jets, are now quiet. The gas has been expelled or consumed. The black holes are still there, but they are no longer visible. Scientists are also searching for dormant black holes through gravitational lensing. When a black hole passes between Earth and a distant star, its gravity bends the star's light, creating a temporary magnification. By monitoring millions of stars, scientists can detect these lensing events and estimate the number of black holes along the line of sight. Early results suggest that dormant black holes outnumber active ones by factors of hundreds or thousands. The black holes we see with telescopes are the exception, not the rule. Most black holes are hidden, invisible, and completely undetectable with current technology. This hidden population has profound implications for galaxy evolution. Dormant black holes still exert gravitational influence. They anchor the centers of galaxies, stabilize orbits, and influence the distribution of stars and gas. Even when not feeding, they shape their environments. Dormant black holes can also reactivate. If gas falls into a galaxy from the intergalactic medium, or if the galaxy merges with another, the dormant black hole will wake up. It will begin feeding again, launching jets and heating gas. The reactivation can be sudden and violent, transforming a quiet galaxy into an active one in just a few million years. The James Webb Telescope is observing galaxies in various stages of reactivation. Some are just beginning to show signs of activity, with faint jets and weak emission lines. Others are in full eruption, with powerful jets and bright cores. By studying these galaxies, scientists can understand the triggers and timescales of black hole reactivation. The hidden population also includes intermediate mass black holes. These are black holes with masses between 100 and 100,000 times our star. They are too massive to form from single stars, but too small to be supermassive. Scientists believe they form through the merger of smaller black holes or the direct collapse of star clusters. Intermediate mass black holes are especially hard to detect. They are rare, scattered across galaxies, and often dormant. The James Webb Telescope is searching for them by observing dense star clusters and the centers of dwarf galaxies. So far, only a handful have been confirmed. The discovery of a large hidden population of black holes would change our census of the universe. It would mean that black holes contribute more to the total mass of galaxies than previously thought. It would also mean that the universe is more dangerous than it appears. Invisible black holes could lurk anywhere, undetectable until something falls into them. The James Webb Telescope is peeling back the darkness. It is revealing black holes that were hidden for billions of years. And with every discovery, the universe becomes a little less mysterious and a little more strange. The galaxies we see today will not last forever. Over billions of years they will merge, collide, and reshape themselves into forms we can barely imagine. The James Webb Telescope is showing us snapshots of this future by observing galaxies in the early universe, where mergers are common and violence is the norm. Our own galaxy is on a collision course with Andromeda. In about 4 billion years, the two galaxies will begin to merge. Stars will pass by each other without colliding, but the gas clouds will smash together, triggering massive bursts of star formation. The night sky will be ablaze with new stars. At the centers of the merging galaxies, the supermassive black holes will spiral toward each other. The process will take hundreds of millions of years. As they get closer, they will release gravitational waves, ripples in space-time that will propagate across the universe. Finally, they will merge in a cataclysmic event that will shake the fabric of reality. The merged black hole will be more massive than either of its parents. It will launch jets that sweep through the combined galaxy, heating gas and shutting down star formation. Within a few 100 million years, the merged galaxy will become a red nugget, filled with old stars and devoid of new ones. This is the fate of most galaxies. Merge, form stars, quench, and fade. The James Webb Telescope is observing every stage of this process in distant galaxies. It is showing scientists what our galaxy will look like billions of years from now. But not all galaxies merge. Some remain isolated, drifting through intergalactic space without encountering neighbors. These galaxies evolve more slowly. They continue forming stars for longer periods, sustained by gas flowing in from the intergalactic medium. But eventually, they too will exhaust their fuel and go dark. The ultimate fate of all galaxies is the same: darkness. The stars will die, the gas will be expelled, and the galaxies will become graveyards of dead stars orbiting invisible black holes. This process will take trillions of years, far longer than the current age of the universe. But it is inevitable. The James Webb Telescope is also revealing the fate of galaxy clusters. These are groups of hundreds or thousands of galaxies bound together by gravity. Over time, the galaxies within clusters merge, forming a single giant elliptical galaxy at the cluster's center. The process is slow but relentless. In the most extreme cases, entire clusters merge. The result is a supercluster, a structure containing tens of thousands of galaxies spanning hundreds of millions of light years. The James Webb Telescope has observed several of these merging superclusters in the early universe, showing that large-scale structure formation is an ongoing process. The mergers are not always clean. Sometimes galaxies collide at high speeds, passing through each other without merging. The encounter disrupts both galaxies, triggering star formation and launching tidal tails of stars into intergalactic space. The James Webb Telescope has captured several of these high-speed collisions, revealing their chaotic aftermath. The future of galaxies is also tied to the expansion of the universe. As space expands, galaxies that are not gravitationally bound drift apart. Eventually, distant galaxies will recede so fast that their light can no longer reach us. They will disappear beyond the cosmic horizon, lost to observation forever. This process is already happening. Galaxies in the distant universe are receding at velocities greater than the speed of light, carried away by the expansion of space itself. The James Webb Telescope can see some of these galaxies, but only because their light was emitted billions of years ago when they were closer. In the far future, billions of years from now, observers in our galaxy will see a universe that is much emptier. Only the galaxies in our local group, bound together by gravity, will remain visible. The rest of the universe will have disappeared, swallowed by the expanding void. The James Webb Telescope is giving us a glimpse of this future. It is showing us how galaxies evolve, merge, and eventually fade. It is revealing that the universe is not eternal. Everything has a beginning and an end. But before the end comes, there is still so much to discover. The James Webb Telescope has answered some of the biggest questions in astronomy. But for every question it answers, it raises 10 more. The universe is revealing its secrets slowly, and each discovery opens new mysteries that demand explanation. One of the biggest unanswered questions is how the first black holes formed. The little red dots and the starless monster suggest that direct collapse was common in the early universe. But scientists still do not understand the exact conditions required for direct collapse. How massive must a gas cloud be? How much radiation is needed to prevent fragmentation? These questions remain unsolved. Another mystery is the role of black holes in galaxy formation. Did black holes form first and seed galaxies? Or did galaxies form first and create black holes? The James Webb Telescope has found evidence for both scenarios, suggesting the answer may vary depending on the environment. But a unified theory is still missing. The fate of runaway black holes is another open question. The James Webb Telescope confirmed one runaway, but how common are they? Do they remain isolated forever, or do they eventually get captured by other galaxies? And what happens to the stars forming in their wakes? These questions will require decades of observation to answer. The nature of dark matter remains one of the greatest mysteries in physics. If primordial black holes are dark matter, it would solve one puzzle but create others. How many primordial black holes exist? What is their mass distribution? And why have we not detected more of them through gravitational lensing? The James Webb Telescope is providing clues, but definitive answers are still out of reach. The behavior of black hole jets is another area of uncertainty. Why do some jets wobble while others remain stable? What determines the power and duration of jets? And how do jets interact with the gas in their host galaxies? The James Webb Telescope is observing jets in unprecedented detail, but the underlying physics is still not fully understood. The transition from little red dots to quasars is also poorly understood. Scientists know that black holes shed their gas cocoons and become visible as quasars, but the exact process is unclear. How long does the transition take? What triggers it? And what happens to the gas that is expelled? These questions are active areas of research. The merger dynamics of triple black hole systems are another frontier. The James Webb Telescope observed the aftermath of a triple interaction, but scientists want to see the process as it happens. Gravitational wave detectors may soon catch the signals from merging black holes, providing real-time data on the dynamics. But observing the optical and infrared counterparts will require coordination between multiple telescopes. The existence of intermediate mass black holes is still uncertain. The James Webb Telescope is searching for them, but they are rare and hard to detect. If they exist in large numbers, they could fill a critical gap in our understanding of black hole formation. But if they are rare, it would suggest that black holes form through only a few pathways. The long-term evolution of galaxies is another area where more data is needed. The James Webb Telescope has observed galaxies at various stages of evolution, but scientists want to track individual galaxies over time. This is impossible with current technology, but future telescopes may be able to monitor galaxies continuously, revealing how they change over millions of years. The role of black holes in cosmic reionization is also debated. Reionization is the process by which the universe transitioned from neutral hydrogen to ionized hydrogen about 13 billion years ago. Scientists believe that radiation from the first stars and black holes drove this transition, but the exact contribution from black holes is unknown. The James Webb Telescope is observing the era of reionization, providing new constraints on the role of black holes. The possibility of life around orphaned stars is another intriguing question. If planets form in the tail of the runaway black hole, could they support life? The environment is harsh, but not impossible. The James Webb Telescope cannot answer this question directly, but it can search for biosignatures in the atmospheres of exoplanets around other stars, providing insight into the conditions necessary for life. Finally, the ultimate fate of the universe remains uncertain. Will the expansion continue forever, leading to a cold, dark future? Or will some unknown force reverse the expansion, causing a big crunch? The James Webb Telescope is measuring the expansion rate and the distribution of matter, helping scientists refine their models. But the final answer may not come for decades. The James Webb Telescope has opened a new chapter in astronomy. It has shown us the early universe in exquisite detail, revealing black holes, galaxies, and cosmic events that challenge our understanding. But the journey is just beginning. Every image, every spectrum, every discovery brings new questions. And those questions drive the next generation of telescopes, the next wave of research, the next leap in understanding. The universe is vast and strange, and we have only scratched the surface. But what we have found so far is extraordinary. Black holes do not exist in isolation. They are nodes in a vast cosmic web, connected by filaments of gas and dark matter that stretch across billions of light years. The James Webb Telescope is mapping this web, revealing how black holes influence structure on the largest scales imaginable. The cosmic web formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average pulled in more matter through gravity. Over billions of years, this matter collected into filaments, with galaxies forming at the intersections. Black holes formed at the centers of those galaxies, anchoring the web's nodes. The James Webb Telescope can see the filaments. They glow faintly in infrared light, heated by radiation from nearby galaxies and black holes. The filaments are not uniform. They vary in density and temperature, creating a complex network that looks like a neural network or a spider web. Black holes shape the web by heating gas. When black holes feed, they launch jets and winds that heat the surrounding intergalactic medium to millions of degrees. This hot gas cannot collapse into new galaxies. It remains in the filaments, filling the space between nodes and preventing further structure formation. The heating process is self-regulating. When too many black holes become active, they heat too much gas, shutting down galaxy formation. This reduces the supply of gas to black holes, causing them to become dormant. Over time, the gas cools and the cycle repeats. The cosmic web pulsates with activity, driven by the feedback between black holes and their environment. The James Webb Telescope has observed this feedback in action. Galaxies in dense regions of the web, where multiple filaments intersect, tend to have more active black holes. Galaxies in sparse regions have quieter black holes. The web's structure directly influences black hole activity. The filaments also act as highways for galaxy mergers. Galaxies move along the filaments, drawn by gravity toward the densest nodes. When they reach the nodes, they collide and merge, triggering bursts of star formation and black hole activity. The James Webb Telescope has captured several of these collisions happening at the intersections of filaments. The cosmic web is not static. It evolves over time as galaxies move, merge, and form new structures. In the early universe, the web was less defined. Filaments were thinner and nodes were smaller. The James Webb Telescope's observations of the early web show a universe in the process of organizing itself. Over billions of years, the web has become more pronounced. Filaments have grown thicker as gas accumulates. Nodes have grown more massive as galaxies merge. The largest nodes, called galaxy clusters, contain thousands of galaxies and are the most massive structures in the universe. Black holes at the centers of these clusters are among the most massive known. Some exceed 10 billion times the mass of our star. They dominate their environments, controlling the flow of gas and the formation of stars across the entire cluster. The James Webb Telescope is studying these giant black holes to understand how they grew so large. The cosmic web also contains voids. These are regions with almost no galaxies, stretching hundreds of millions of light years across. Black holes in galaxies near the edges of voids have different feeding patterns than those in dense regions. They tend to be less active, starved of gas by the emptiness around them. The James Webb Telescope is comparing black holes in different environments to understand how location affects their evolution. Early results suggest that environment matters enormously. Black holes in clusters grow faster and become more massive than those in voids. The cosmic web determines the fate of black holes. But the web itself is temporary. As the universe expands, The filaments stretch and thin. The nodes drift apart. Eventually, billions of years from now, the web will dissolve. Galaxies will become isolated, separated by vast distances that light cannot cross. The cosmic web is a phase, not a permanent structure. The James Webb Telescope is capturing the web at its peak. It is showing us the universe when structure is most pronounced, when connections are strongest, when black holes are most active. This is the golden age of the cosmic web, and we are witnessing it in real time. Black holes consume matter and convert it into energy with terrifying efficiency. When gas spirals into a black hole, it heats up and radiates. Up to 40% of the gas's mass can be converted into radiation before it crosses the event horizon. This is far more efficient than nuclear fusion, which converts less than 1% of mass into energy. The energy released by feeding black holes powers some of the brightest objects in the universe. Quasars, the brilliant cores of active galaxies, shine with the light of trillions of stars. All that energy comes from black holes, no larger than our solar system. The James Webb Telescope has observed quasars across cosmic time, revealing how their energy output has changed. In the early universe, quasars were everywhere. The James Webb Telescope found them in nearly every deep field image, scattered across the sky like stars. These ancient quasars were powered by black holes feeding at extreme rates, consuming gas faster than the Eddington limit should allow. But quasars are temporary. They shine brightly for a few 100 million years, then fade as the gas runs out. The James Webb Telescope is observing quasars at different stages of their life cycle, from young quasars just beginning to shine to old quasars in their final dimming phase. The energy from quasars does not just disappear. It heats the surrounding gas, ionizes atoms, and drives winds across entire galaxies. This energy feedback regulates galaxy formation. Without it, galaxies would form too many stars and grow too large. The energy from black holes keeps galaxies balanced. But there is a problem. Scientists call it the energy crisis. The total energy released by all the black holes in the universe should be enough to heat all the gas in the intergalactic medium to billions of degrees. But observations show that most of this gas is only a few 100,000 degrees. Where is the missing energy? One possibility is that the energy escapes into voids, regions of space with almost no matter. The voids act as sinks, absorbing energy without heating much gas. The James Webb Telescope is testing this theory by measuring the temperature of gas in different environments. Another possibility is that the energy is converted into turbulence. Instead of heating gas uniformly, black hole jets create swirling motions that dissipate over time. The James Webb Telescope has detected turbulent gas in several galaxies, supporting this theory. A third possibility is that the energy measurements are wrong. Scientists estimate black hole energy output by observing their radiation and jets. But if black holes are consuming matter more slowly than assumed, or if some energy is escaping as gravitational waves instead of light, the total energy output could be lower. The James Webb Telescope is helping resolve the energy crisis by measuring black hole feeding rates directly. By observing the gas spiraling into black holes and calculating its temperature and velocity, scientists can determine how much energy is being released. Early results suggest that previous estimates were too high. The energy crisis also affects our understanding of cosmic reionization. During reionization, the universe transitioned from neutral hydrogen to ionized hydrogen. This process required enormous amounts of energy. Scientists believe that radiation from the first stars and black holes provided this energy. But if black holes release less energy than assumed, other sources must have contributed. The James Webb Telescope is observing the era of reionization directly, measuring the ionization state of gas in the early universe. The data show that reionization happened faster than models predicted. This suggests that black holes were more energetic in the early universe than they are today. But the energy crisis is not just about the past. It affects predictions for the future. If black holes release less energy than expected, galaxies will continue forming stars for longer periods. If they release more energy, star formation will shut down earlier. The James Webb Telescope's measurements will refine these predictions. The energy from black holes also affects the formation of the cosmic web. The filaments that connect galaxies are heated by black hole radiation. If the energy output is too high, the filaments evaporate. If it is too low, the filaments collapse and form new galaxies. The balance is delicate. The James Webb Telescope is revealing that the universe is powered by black holes. Their energy shapes galaxies, regulates star formation, and maintains the cosmic web. Understanding this energy is essential to understanding the universe itself. And the more scientists measure, the more complex the picture becomes. Every time black holes merge, they shake the fabric of space-time. Gravitational waves ripple outward at the speed of light, carrying energy and information across the cosmos. The James Webb Telescope cannot detect these waves directly, but it can see their effects and identify the systems that will produce them in the future. Gravitational wave detectors on Earth have already caught signals from dozens of black hole mergers. Most involve black holes with masses between 10 and 100 times our star. These are stellar mass black holes, formed from the collapse of massive stars. When they merge, they release gravitational waves that last only a few seconds. But supermassive black hole mergers are different. They release waves that last for months or years, with wavelengths too long for Earth-based detectors to catch. Scientists need space-based detectors to observe these events. The James Webb Telescope is identifying the systems that will eventually produce these gravitational waves. The Cosmic Owl Galaxy is one example. The two black holes in the galaxy are spiraling toward each other, slowly losing energy to gravitational radiation. In a few 100 million years, they will merge. The resulting gravitational wave signal will be among the strongest ever detected, visible to instruments anywhere in the universe. The James Webb Telescope is also observing galaxies where black hole mergers have recently occurred. These galaxies show signs of disruption, with gas and stars scattered in chaotic patterns. The gravitational waves from these mergers have already passed through Earth, but they occurred billions of years ago, before detectors existed to catch them. By studying these post-merger galaxies, scientists can understand what happens after black holes collide. The merged black hole is often offset from the galaxy's center, kicked by the asymmetric release of gravitational waves. This kick can be strong enough to send the black hole wandering through the galaxy, or even eject it entirely. The James Webb Telescope found evidence of these kicks in several galaxies, black holes displaced from their central positions, surrounded by disrupted gas. These displaced black holes eventually sink back to the center through a process called dynamical friction, but it takes hundreds of millions of years. Gravitational waves also carry information about the black holes that produce them. By analyzing the wave pattern, scientists can determine the masses and spins of both black holes. They can reconstruct the orbital dynamics and calculate how much energy was released. The waves are messengers, telling the story of cosmic collisions. The universe is filled with gravitational waves. Every black hole merger, every neutron star collision, every violent event involving massive objects produces waves. These waves overlap, creating a background hum of gravitational radiation. Scientists call it the gravitational wave background. Future detectors will measure this background, revealing the cumulative history of black hole mergers across cosmic time. The James Webb Telescope is helping by identifying which galaxies are likely to host merging black holes. By combining optical and infrared observations with gravitational wave data, scientists can build a complete picture of black hole evolution. The merger of supermassive black holes is one of the most energetic events in the universe. In a few seconds, the final plunge releases more energy than all the stars in the observable universe emit in a year. That energy does not come from matter. It comes from the warping of space-time itself. The James Webb Telescope is observing galaxies where these mergers will happen soon, in cosmic terms. Systems where black holes are separated by only a few hundred light years, spiraling closer every million years. These are the laboratories of the future, where the next generation of gravitational wave detectors will focus their attention. Gravitational waves are opening a new window on the universe. Combined with observations from the James Webb Telescope, they provide a complete view of black hole mergers. Not just the final seconds, but the entire process, from initial approach to final collision. The universe is louder than we thought. It hums with gravitational radiation, echoing with the violence of black holes colliding across billions of light years. The James Webb Telescope is showing us where to listen, and when we listen carefully, we hear the universe roaring. The James Webb Telescope was designed to see the first stars and galaxies that formed after the Big Bang. It was built to capture first light, the moment when the universe emerged from the cosmic dark ages and began to glow. And it has succeeded beyond all expectations. The cosmic dark ages began about 400,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before that, the universe was a hot plasma, opaque to light. After atoms formed, the universe became transparent. But there were no stars yet. The universe was dark. This darkness lasted for hundreds of millions of years. Then, in pockets of space where gas was densest, the first stars ignited. They were massive, hundreds of times the mass of our star, burning hot and bright. They lived fast and died young, exploding as supernovas within a few million years. The James Webb Telescope has detected light from this era, distant galaxies, so far away that their light has been travelling for over 13 billion years. These are not the very first stars, but they are close. They formed less than 500 million years after the Big Bang, when the universe was still in its infancy. These early galaxies are strange. They are smaller and more chaotic than modern galaxies. They contain massive stars burning through their fuel at extreme rates. They are dominated by black holes that formed through direct collapse. They are laboratories of creation, forging the elements that would later build planets and life. The light from these galaxies has been stretched by the expansion of the universe. What was once ultraviolet light is now infrared, shifted to longer wavelengths by 13 billion years of cosmic expansion. The James Webb Telescope was designed specifically to detect this shifted light. By analysing the spectra of early galaxies, scientists can determine their composition. The first galaxies contained almost no heavy elements. They were made of hydrogen and helium, the primordial elements created in the Big Bang. But each generation of stars added more heavy elements, enriching the gas and changing the chemistry. The James Webb Telescope is tracking this chemical evolution. It is measuring the abundance of carbon, oxygen, nitrogen, and other elements in galaxies at different epochs. The data show that heavy elements appeared faster than expected. The first stars were more efficient at producing and dispersing these elements than models predicted. The first galaxies also hosted the first black holes. Some of these black holes were born from direct collapse, as described in earlier chapters. Others formed from the deaths of the first stars. The James Webb Telescope has found black holes in galaxies less than 600 million years after the Big Bang. They are already massive, hundreds of millions of times our star. This rapid black hole growth challenges traditional theories. If black holes formed from stellar deaths, they should be smaller at early times. But the observations show otherwise. The black holes in the earliest galaxies are disproportionately massive. Direct collapse offers an explanation, but scientists are still testing this theory. The first light also marks the beginning of reionization. The radiation from the first stars and black holes began to ionize the hydrogen gas filling the universe. This process transformed the cosmos from neutral to ionized, making it transparent to certain wavelengths of light. The James Webb Telescope is observing galaxies during reionization, capturing the transition in action. The data reveal that reionization was not uniform. Some regions ionized quickly, driven by clusters of early galaxies. Other regions remained neutral for longer. The James Webb Telescope is mapping these ionized bubbles, showing how they grew and merged over hundreds of millions of years. First light was not a single moment. It was a process that unfolded over cosmic time. The James Webb Telescope is revealing this process in exquisite detail, showing how the universe transitioned from darkness to light, from simplicity to complexity, from a smooth sea of hydrogen to a rich tapestry of galaxies and stars. The first galaxies were violent places. Stars formed and died rapidly. Black holes consumed gas at extreme rates. Supernovas and gamma-ray bursts lit up the sky. The James Webb Telescope is showing us this violence, revealing the chaos that built the universe we see today. Every deep-field image from the James Webb Telescope contains thousands of galaxies. Many of them are from the era of first light. Each one is a time capsule, preserving the conditions of the early universe. And each one tells a story of creation. The universe began in darkness, but it did not stay dark for long. Black holes are paradoxes. They are solutions to Einstein's equations, yet they violate some of the fundamental principles of physics. They destroy information, create singularities, and warp space-time in ways that challenge our understanding of reality. The James Webb Telescope is observing black holes in unprecedented detail, and every observation deepens the paradox. The most famous paradox is the information paradox, proposed by Stephen Hawking. According to quantum mechanics, information cannot be destroyed, but black holes destroy everything that falls into them. The information about the particles that cross the event horizon seems to vanish forever. This violates a fundamental law of physics. Hawking later proposed that black holes emit radiation, now called Hawking radiation. This radiation carries away energy, causing the black hole to slowly evaporate. That the radiation is thermal, carrying no information about what fell into the black hole. The paradox remains unresolved. The James Webb Telescope cannot detect Hawking radiation. It is far too weak to observe from Earth. But the telescope is studying black holes in other ways, searching for clues about how information might be preserved. Some theories suggest that information is encoded on the event horizon itself, in quantum fluctuations too small to see. Another paradox involves the singularity at the center of a black hole. According to general relativity, all the mass of a black hole is compressed into a single point of infinite density. But infinity is not a physical quantity. It is a sign that the equations have broken down. Something is missing from our understanding. Quantum mechanics may provide the answer. At extremely small scales, quantum effects become important. Some theories suggest that the singularity is not a point, but a tiny quantum object, governed by laws we do not yet understand. The James Webb Telescope cannot see inside black holes, but it can test the predictions of these theories by observing black hole behavior. The firewall paradox is another puzzle. Some theories predict that a wall of high-energy particles exists just inside the event horizon, incinerating anything that crosses it. But this contradicts the principle of equivalence, which says that falling into a black hole should feel no different than floating in empty space. The paradoxes are piling up. The James Webb Telescope is observing matter just outside black hole event horizons, in the accretion disks and jets. This matter is experiencing extreme conditions, stretched by tidal forces and heated to billions of degrees. By studying this matter, scientists hope to learn about the environment near the event horizon. The observations show that matter behaves strangely near black holes. It forms spirals and vortices. It emits radiation in patterns that suggest magnetic fields are twisted into complex shapes. The data match some predictions of general relativity, but not others. The theory is incomplete. Black holes also challenge our understanding of time. Time slows down near a black hole, and at the event horizon, it stops entirely from the perspective of a distant observer. But from the perspective of someone falling into the black hole, time continues normally. This creates a paradox where two equally valid perspectives give contradictory results. The James Webb Telescope is measuring time dilation effects by observing the motion of gas near black holes. The gas appears to slow down as it approaches the event horizon, stretched out by the warping of space-time. But the observations also reveal that the gas experiences turbulence and instability, suggesting that time dilation is not the only effect at play. Another paradox involves the growth of supermassive black holes. The James Webb Telescope found black holes in the early universe that are too massive to have formed through normal processes. They grew too fast, exceeded theoretical limits, and appeared too early. Either the theories are wrong, or something extraordinary happened in the early universe. The observations from the James Webb Telescope are forcing scientists to reconsider fundamental assumptions. Maybe black holes do not destroy information. Maybe singularities do not exist. Maybe the event horizon is not what we think it is. The telescope is providing data that challenge the foundations of physics. Black holes are tests of our theories. They push the limits of what we can understand. The James Webb Telescope is observing these tests in action, revealing phenomena that do not fit into neat categories. And with every observation, the paradoxes deepen. The universe is not obligated to make sense to us. It follows its own rules, indifferent to our confusion. The James Webb Telescope is showing us those rules, even when they contradict everything we thought we knew. And that is exactly what science needs. The James Webb Space Telescope has been operating for less than 3 years, but it has already transformed our understanding of the universe. It has revealed black holes exploding with unimaginable violence, galaxies forming in the cosmic dawn, and structures that challenge the limits of physics. But its legacy extends beyond the discoveries it has made. The telescope has proven that ambitious science is possible. It took 30 years to design, build, and launch. It cost $10 billion. It required the collaboration of thousands of engineers, scientists, and technicians across multiple countries. And it worked. Against all odds, it worked perfectly. The James Webb Telescope is a monument to human ingenuity. It sits 1 million miles from Earth, in a region of space where the gravitational pull of Earth and the Moon balance out. It maintains its position using tiny thrusters, firing occasionally to counteract the gentle push of sunlight. It is a miracle of engineering. The telescope's primary mirror is 21 feet across, made of 18 hexagonal segments coated in gold. The gold reflects infrared light efficiently, allowing the telescope to see the faint glow of distant galaxies. The mirror is so precise that its surface deviates from perfect by less than 1/10,000th the width of a human hair. Behind the mirror is a sun shield the size of a tennis court. The shield blocks heat and light from the stars, keeping the telescope's instruments cold enough to detect faint infrared signals. The temperature difference between the sun-facing side and the telescope side is over 500 degrees. The sun shield is a barrier between fire and ice. The instruments on the telescope are marvels of technology. They can split light into spectra with thousands of wavelengths, revealing the chemical composition of objects billions of light years away. They can capture images with resolution so sharp that individual stars in distant galaxies become visible. They can observe the universe in wavelengths of light invisible to human eyes. The James Webb Telescope has observed over 15,000 objects in its first 3 years. Galaxies, stars, planets, asteroids, comets, nebulae, black holes, and more. Every observation adds to the collective knowledge of humanity. Every image reveals something new. But the telescope's greatest legacy may be the questions it has raised. Before the James Webb Telescope, scientists thought they understood how galaxies formed. The telescope showed them they were wrong. Before the James Webb Telescope, scientists thought black holes grew slowly. The telescope revealed they can grow explosively. Every answer leads to new mysteries. The next generation of astronomers will build on this legacy. They will use the data from the James Webb Telescope to design new missions, new instruments, and new theories. They will push further into the unknown, driven by the discoveries of this telescope. The James Webb Telescope has also inspired millions of people around the world. Its images have been shared on social media, featured in museums, and taught in classrooms. They remind us that the universe is vast, beautiful, and full of wonders we are only beginning to understand. Children who see these images today may become the scientists of tomorrow. They may design the telescopes that succeed the James Webb. They may solve the mysteries it has uncovered. They may venture into space themselves, carrying humanity to the stars. The telescope's mission is expected to last at least 20 years, but its impact will last far longer. The data it collects will be analysed for decades. The discoveries it makes will be studied for generations. The questions it raises will drive science for centuries. The James Webb Telescope is more than a machine. It is a symbol of what humanity can achieve when we work together toward a common goal. It is a reminder that curiosity is one of our greatest strengths. It is proof that the universe rewards those who seek to understand it. The black holes we have explored in this journey are real. The galaxies are real. The explosions, the mergers, the runaway giants, all of it is real. The James Webb Telescope has shown us a universe more violent, more beautiful, and more strange than we ever imagined. And we are only at the beginning. The telescope is still observing. It is still discovering. It is still revealing secrets hidden for billions of years. Every week brings new data. Every month brings new insights. The universe is unfolding before our eyes. The James Webb Space Telescope captured a black hole explosion. It showed us galaxies being destroyed and created. It revealed the birth of the first black holes and the death of entire galaxies. It changed everything we thought we knew, and it is still changing everything. The journey continues. The discoveries continue. The universe continues to surprise us, and the James Webb Space Telescope continues to show us wonders beyond imagination. This is just the beginning of what we will learn. The universe has so much more to reveal, and we are ready to listen.